In terms of detailed quantitative analysis, our focus is definitely going to be on first order RC and RL circuits. However, I do want to briefly mention second order circuits. So our second order circuits come about if we have resistors, inductors, and capacitors all in the same circuit. So we would call such a circuit an RLC circuit. In the slide here, I have a simple series RLC circuit. We could also consider a parallel RLC circuit where each of the components are in parallel with one another. And then, of course, there are ways to analyze more complicated circuits where the elements aren't all in series or all in parallel. But again, I just want to give a rough overview at the moment to how to set that up. So here is our second order circuit from the previous slide. And again, we have switching action just like we saw before, because in this chapter, ultimately we are concerned with the transient response, which arises from switching. And so we could start by doing KVL. So I've implicitly put voltage polarities such that our current is always going through a voltage drop as we go around this loop. So we get our inductor voltage plus our resistor voltage plus our capacitor voltage is equal to our source voltage Vs. From there, we can use our IV expressions. So we know for our inductor voltage is equal to L di dt. We know for the resistor, we can just use Ohm's law. The voltage is equal to I times R. And for our capacitor voltage, it's just our capacitor voltage Vc of t, and we set that equal to Vs. So notice all of these quantities are values of t. We expect that after the switch has been closed a long time, we'll eventually reach DC steady state. Our inductor will act like a short, our capacitor will act like an open. So again, there's a lot of analysis that we're not going to do completely. So if we were going to derive this expression, there are lots of different ways we could do this, but the one that makes the most sense to me is we could say, well, in this circuit, we have this current moving clockwise. It's the same current through everything. So we could say, really, this current is equal to our capacitor current I sub C. Then we can use our capacitor IV equation, and we can say, well, I sub C is equal to C dV dt, where of course our voltage is our capacitor voltage. Now all we need to do is substitute that expression for the two instances where we have current over here. Again, because this current is equal to our capacitor current because everything is in series. So what we end up with then is a second order derivative. So second derivative of voltage with respect to time. I've also divided through by L so we can get a coefficient of 1 here. So we get RL times the first derivative of our voltage with respect to time, 1 over LC times our voltage, and all that equal to some constant. So again, that's how we get a second order differential equation. We're not going to go through the process of solving it as we did with our first order, but I think it is useful to be aware of. And in the next and final video of this unit, we're going to look briefly about the different types of responses and how our second order circuits differ from our first order circuits.